Because Catherine Guns is not here.
Oh, okay.
postdoc.
I didn't know that. Right.
Yeah.
Okay. She's your postdoc, of course.
So
Where's the
why don't you
list?
do the first couple, but Fernando's not here, the last speaker. So we got to look out for him. And he can still get his, they said if he brings a memory stick or something, just get on.
Okay. Should we
Otherwise,
start?
we'll end early, I guess. What do we do? Have a discussion? Go to lunch? Well, if there's only, I guess we shouldn't worry so much about the time if Fernando doesn't show up.
But if it's the last one.
Okay.
But there are other people from IREO. Yeah, they're not.
But they didn't insert the talk in the lineup.
Okay, welcome back, everyone, for the second. We're on time, aren't we?
My talk's short, so.
Okay. Yeah, the second in the Tectonics session. So we're going to kick off with the first talk, which is the calibration of seismogenic thickness for estimation of seismic moment accumulation rate from strain rate. This will actually be given not by Catherine Guns, but by David Samwell, my co-chair.
Okay, thanks. I can let people wander in a little bit because I think my talk is not that long. I'm hopefully not that long. So what I want to talk about is quite a bit different. I'm not going to show any INSAR results, or just a little bit at the end, but I want to talk about how we interpret surface deformations from geodesy. And one of the main things we'd like to learn from geodesy is how much seismic moment is accumulating in the crust, because if we know the accumulation rate, and we know the time since the last big event, we can say, well, the next earthquake has this moment available for release. And so that's sort of the objective here. And I'll start off showing a motivation slide, but then get into the issue that there are two ways of measuring seismic moment accumulation. There's one using, block models with backslip, measuring the moment on those models. But there's also another method using strain rate, and the strain rate is used to estimate the moment accumulation rate in little cells. And so I'll point out that at least for a model, these two methods should give the same amount of total moment. Model, a perfect thing, so we know what we're putting on the faults, and we know what we're measuring on the surface, and these should match. In order to get them to match, there's a free parameter called the Kostroff layer thickness. Actually, that times the shear modulus, but we don't really know what that number is. People have assumed a number of like 11, but it's based on really old information. So we want to update that number using models, and then use that information to try to estimate how much seismic moment is accumulating away from the major faults using geodesy. And of course, that's very controversial because we don't know where all the faults are, so it depends on your set of faults. But I'll go through some examples, and then finally about how INSAR can be used to maybe improve the whole thing. So here's the motivation here, a paper by Elliott and others showing that the major earthquakes usually occur in areas where the strain rate is greater than about 50 nanostrain per year. And so that's sort of the accuracy that we'd like to get to, 50 nanostrain per year. And that's actually quite a challenge for INSAR. But, and strain rate, as I said, can be converted to moment rate, and then that times the time gives you the total moment. Okay, so as I said before, there are two methods of measuring moment accumulation rate in the crust, and one is this fault-based method, and then the strain-based method, and I'll go through both of those right now. Relatively straightforward. Okay, approach one, fault-based models. And you see the equation here. I guess I don't have a pointer, but you can see it. It shows the moment accumulation rate divided by the length of the fault, because you don't really know how long the rupture is going to be. But the moment accumulation rate divided by the length of the fault is equal to the shear modulus times the velocity of the block velocity, and then times the area, or times the depth of the lock zone. Very simple idea. That's for a single two-dimensional fault, and we can use geodesy, of course, to measure the depth of the lock zone and the slip rate and so on. For a more complicated set of faults associated with the block model, one would simply add up all those contributions to the moment rate. So when we build a model, a backslip model or a viscoelastic type model, we can know exactly how much moment we injected into that model on all the different faults. And I'll be talking about 3 models because the different models have different results. And the 2 types of models I'll talk about, three types of models. One is a pure, just elastic half-space block model, backslip. The second one is an elastic plate over a viscoelastic half-space, a little bit more complicated. It includes the time element. And then our third model would be that same thing, but with variable crustal rigidity to simulate things like low rigidity areas along the Salton Trough, we'll see. Okay, so here are the 3 models that we're using. I'll start with the model on the right first, Zhang and Shen. That's a standard backslip block model, and we can use the numbers from their publication to get the total moment accumulation rate per year, and it's 1.18 times 10 to the 19 Newton meters per year. And so that's a number we can use. The center one is from a paper by Ward et al. It has fewer faults, lots fewer faults, but it's a viscoelastic model. And so in both of these cases, these models are tuned to fit the surface GPS velocities and INSAR in the case of Ward. And in that case, the moment rate is 1.52 times 10 to the 19. And then the one on the left is really just showing that same model, but with variations in crustal rigidity. And you can see low rigidity along the Salton Trough, where the Salton Sea is, and then high rigidity in other places. And this has a pretty big effect on the moment accumulation on those faults. And overall, it has a lower moment accumulation rate. Okay, so that's, that's cool. All right. So that's approach 1, backslip models. We know that. Approach 2 is to measure the strain rate on the surface everywhere and then convert that strain rate into moment rate. But actually, we're measuring a tensor, a 2-dimensional strain rate tensor. So we have to summarize that strain rate in terms of a scalar strain rate or a scalar moment rate. And you can see there are 3 equations here. These are 3 equations put out by Savage and Simpson, 3 ways of summarizing the strain rates into moment rate. They're almost the same, and I'll show you some examples, but there are slight differences here. So this is the second approach. We can just go directly from surface strain rate measurements to moment rate. Okay, those 2 numbers should agree, right? These are models, they're perfect. So we know the fault-based number, we know the strain rate-based number, but the strain rate-based number had an unknown in there, and that's this Kostroff thickness, H. And so we're just going to vary the Kostroff thickness until those 2 numbers match for these 3 models. And you can see the one on the left, this is the uniform rigidity viscoelastic model, I believe, and that requires a thickness of about 11.5 kilometers. The central one is a variable rigidity, 9.7 kilometer thickness, and the one on the right is the block model, 7.3 kilometers. So they give different numbers. In the literature, people tend to use 11. 11 sounds like a great number, but it's just based on a previous publication where they said 11 was good. So this is sort of an unknown in this whole process. So we can now, just using these 3 models, put some bounds on this Kostroff thickness. And basically, it depends a little bit on which moment, going from the tensor to the scalar, depends which equation you use. although those are pretty close, but it depends more on the model. And as you saw before, the variations go from 7.3 to 11, but this is much less than the seismogenic thickness. Normally, people talk about this as the seismogenic thickness, but that's more like 11 to 20 kilometers. So they aren't really the same thing. Okay, part two here is how do we estimate the off-fault moment accumulation? This is something people are really interested in because, of course, in California, all the big earthquakes we've had recently are away from the major faults. So there must be a lot of moment accumulating away from the major faults. And so we can use this approach now to say, we'll calculate the strain rate from, this is all done from GPS. We eliminate the creeping section because that sort of gives the wrong answer. It's not a high moment rate of the creeping section, it's essentially zero. And then we can subtract off, so we take the original GPS velocities, we subtract off the GPS from that particular fault-based model and take the residual and compute the residual moment rate and then see how that compares with the fault-based one. And you can see in these three cases, the uniform rigidity Ward et al. Model has about 41% off-fault moment. The variable rigidity has 43, and the Zhang and Shen has 32. So these are in pretty good agreement, but there's a lot of uncertainties in all this, and I'll go through that next. It turns out that the biggest uncertainty in that whole process is how do you derive strain rate from GPS velocities. This is not straightforward. There's a nice paper by Maurer and Materna that just came out, but there's been other papers. You can give the same people the same GPS velocities and ask them to compute strain rate, and they'll come up with big differences. And it just depends on how much smoothing you inject into that interpolation process. So in this case, we put in sort of a reasonable amount of smoothing, and we got sort of a 17% variation. Okay, so finally, how accurately do we need to measure the surface velocities, and can INSAR contribute to this? And from this diagram here, it sort of says we need 50 nanostrain per year to really make progress here. And 50 nanostrain is 0.5 millimeters over 10 kilometers. 10 kilometers is a pretty big cell. INSAR is giving us much smaller things like a kilometer, but that's not going to help us because it'll come out noisy and have more moment than we expected. Well, we're reaching this sort of 0.5 millimeter a year accuracy from Sentinel-1. This is just an estimate based on the atmospheric noise, and after 8 years, you'd predict about 0.5 millimeters a year of error. So we're getting there. And then maybe I'll skip some of these. This is just putting in a plug for some of the work that we're doing, and Katya will talk about it next, combining GPS and INSAR to really improve the accuracy of the velocity field and ultimately the strain rate measurements. And we're making progress. It's, again, most of the information on the moment rate is coming from the GPS in this case. The INSAR is not really providing that much, but we're working towards that direction. And here's some examples. We decompose the interseismic deformation line of sight in terms of average velocity and an annual term, semi-annual term, co-seismic, post-seismic. I think Katya will talk about these. But the figure on the right shows the uncertainty, or what's left over in that fit. And it's about 0.5, in some places it's about less than 5 millimeters a year RMS. So we're not really getting there. I mean, we're getting there slowly. And again, finally, we want to take those velocities and compute strain rate, and there's different ways of doing this. And wow, that's cool. It doubled the the imagery, but it's you get the point here. With the one on the left, I think is GNSS only, and the one in the center is GNSS and INSAR, and the one on the right is the difference. And back then, when Jawad did this study, he found about 100 nanostrain per year differences, which is too big still to constrain the models. Okay, so in conclusion, we use these 3 published models to estimate the cost trough thickness, and we find values between 11.5 and 7.3 kilometers. Using the same 3 models, we can estimate the off-fault rates of about 41%, 32%. There's a model where the variable rigidity has less moment accumulation rate because the Salton trough is sort of weak and it doesn't accumulate moment as fast as a uniform rigidity. And then there's an issue with how do you define faults? How many faults do you have in your model? If you put more faults in, you're going to get less off-fault accumulation rate. And of course, the geologists have been telling us that for years. And the biggest uncertainty in this whole process is still, how do you interpolate the velocity fields to get smooth grids of velocity and then strain rate? So I guess I'll end there and take questions.
Thanks. So yes, we have time for a few questions. Tim.
Sorry, I was sitting with the most inaccessible bit of the theatre. Thank you, that's a great presentation. I have lots of questions, so hopefully we can catch up properly later. But the one was about your cost trough thickness kind of equivalent. What does that really mean then, do you think? I mean, I guess there's a question of whether it's, well, maybe you answer that question and then I've got a follow-up.
So I didn't explain that very well, but in that cost trough, the figure's missing. Okay, so there's a figure that you can't see, and and it's a polygon with a uniform thickness, and the corners are being perturbed by something. It's straining, so that whole volume is straining. So it's the area of that times the thickness times the shear modulus is the moment accumulation, basically.
Yeah, yes. So I guess I meant, what does it really, how should we physically interpret that thickness? Because obviously it's basically saying that's the equivalent thickness of moment rates. You know, so, but the earthquakes are rupturing a bigger thickness. So what does it really mean, I guess?
You know, in the literature, some people call that the seismogenic thickness, but the numbers don't match up. And then because the numbers don't match up, they say, well, there's some surface creep, so we can remove that little bit, and maybe there's slip on the bottom, so we can remove that and match the numbers. But yeah, it's a fudge factor. This is what Steve Ward calls it. It's just a fudge factor to make everything work.
And I guess the other thing that could be a fudge factor would be time varying, but I'm asking too many questions, so I should let somebody else go.
Yeah, while you pass the microphone to Ekbal, one comment on that. I mean, it's right, it doesn't agree with the seismogenic thickness, but I notice as you introduce more realism into your models, it gets steeper, right? So is it just actually that we don't have enough?
Maybe, yeah.
David, I wonder if you comment on the non-heterogeneous moment accumulation rate with depth. You sort of did that by removing the creep at the top, but we know that strain is released in a non-heterogeneous way, so it's probably right to assume that it's accumulated in a non-heterogeneous way. And how will that affect your calculations?
So I think the strain rate to moment thing is very approximate. It's, there are going to be variations in the thickness of this layer that's accumulating stress, and then at the faults it might be different than away from the faults. So it was just an approximation that was useful for getting moment rate.
Eric, you have the microphone?
Yeah, and you're assuming this cost trough thickness is the same for the whole of California, even though there's huge variations in crustal thickness?
Yeah, I mean, that's what people have done. Yeah.
Yeah, one more quick question from Paul. Oh, sorry, Laura's already got a microphone.
Hi, good.
You go first.
Do you think that the strain rate should equal the moment rate? And I'm thinking about places where strain rates are incredibly low, if non-existent, and we still get big earthquakes.
So there are places where it doesn't work at all. A top to bottom creeping fault has no moment accumulation, and yet if we use that methodology, we'd find a huge strain rate. So, yeah.
So, Dave, just a very quick question on the off-fault strain. So, of course, you could see earthquakes like ridge crests seem to show up prominently in some of those plots. But I guess my question is, it looked like the boxes, the size that you were, calculating that over was fairly coarse.
Yeah.
And it seems, I think when we think of off-fault strain, we're really thinking of kind of small fractures in some kilometers within distance of a fault. So I guess I wonder how well you can resolve that scale.
So those blocks were made large because if you make them very small, you'll end up with velocities that create high strain, plus or minus everywhere. So it's pretty artificial. You better get going.
Yeah, next door. That's great. You going to introduce?
No, I try.
Okay, so the next talk is going to be Consensus INSAR Time Series and Velocity Model for Southern California by Katya.
Hi, my name is Katya Timofeeva, and I am from NASA JPL, and I'm going to tell you about this collaboration that we've had to create a consensus INSAR time series and velocity model over Southern California. So we have quite a few, if you look at the slide, quite a few participants in our group and quite a few different research institutions that are participating in this exercise, and I'll try to tell you all about it. Some of them are in this room, so thanks for that. This is how we started. Our goal is really to provide a self-consistent and well-documented set of products, namely INSAR velocities and time series, and also GPS velocities and time series, but this group in particular and this talk will be focused on INSAR over Southern California, and the word Southern is in brackets because we're rapidly expanding, as David kind of hinted, to cover the entire plate boundary here, there in the western, northwestern America. That's the primary thing that we've committed to, but really what we really enjoy doing is comparing different existing methods for INSAR processing and post-processing and error correction, and trying to figure out some best practices, trying to figure out what the different impacts the different methods have on our results, and generally trying to put together some kind of consensus. Because if there's something that we've seen so far in this meeting and many other meetings, is that everybody has their own way of making INSAR time series. That's just true. So we have this exercise going on where we compare all of our methods and results, and it's been really fun and interesting. So we began as part of SCAC, Southern California Earthquake Center, and we're trying to put together this community geodetic model. SCAC has several community models: rheology, stress, fault. We're the geodesists. And here on the right, you see our first result. That's from a few years ago. It's just one test, one track, one frame from a Sentinel track, number 71, over Southern California, descending track. And it is obtained from a combination of results, since we're trying to build a consensus, of 5 different research groups at the time. We've expanded a bit since. So you see in this consensus model, and I will tell you in a minute how we got here, that the colors, of course, are INSAR displacements in the line of sight, and there are colored circles also, which are also in the line of sight, but GNSS measurements, both campaign and continuous velocities over the same time period. And I think the agreement is generally pretty good. The places where the agreement is not so good are mostly where there are local effects affecting the GPS velocities, and also where there are nonlinear effects affecting the velocities overall, and there's some disagreement between how the INSAR and GPS velocities were calculated. So for example, here, oh no, spoilers, here. There is some disagreement over there, and that's a big aquifer that's moving up and down with a seasonal signal, big seasonal signal, so the velocities just don't agree between GPS and INSAR. Otherwise, the agreement is very good, which is maybe surprising because we didn't actually constrain the INSAR, as many people do, to conform to the GNSS velocities. So this agreement is pretty natural due to other corrections that we're applying. So how did this come about? So these were the 5 participating groups and their 5 different results. For each of them, there are 2 results. One of them is the velocity, and the other is what would happen if you averaged all these velocities together, which is how we actually get our consensus model. And on the right for each group is a plot that is a difference from the mean model for each of them. So you could see how much they deviate from each other, basically. And there's a whole big summary of the different methods that were used and their pros and cons by all the different groups. And you can see that there are a lot of people have tried many different things, many different corrections. Processing softwares are different. People apply DM corrections, various kinds of atmospheric corrections, phase closure masking, things like that. Each of them, of course, have some impact on the results that you will get at the end for your time series and velocities. And as I mentioned, our consensus model is actually just a simple average of all of these results. However, what that does, and hopefully we can convince ourselves and you of that, is that it will average out these artifacts that come about as a result of the different processing methods that are used in each of these cases. So once we have created our consensus model, which I showed on the first slide, again, we're trying to convince ourselves that a combined model is better than individual models, and we're doing that by validation against GNSS, which again, sometimes it's a good idea and sometimes it's not, but in this case, for most points, it ends up working quite well. So in rows 1 and 3, there are comparisons between the different individual solutions from the different groups. They're just plotted in different colors. But in rows 2 and 4, there are corresponding what happens if you collapse all these solutions into one, and you compare it to the GNSS time series. So if you spend some time looking at this closely, you can also convince yourself that the combined model is better than the individual ones. This is where we are now. We have expanded and we are continuing to expand. So this is our current consensus model. It is now 4 tracks, ascending and descending. And we're spanning the time period between 2015 and 2019. And the reason that we stop at 2019 is because there was an earthquake. There were 2 earthquakes, actually, a whole sequence of them, in Southern California at Ridgecrest. And the biggest challenge that we currently face right now is how to create a time series that spans that earthquake, because it's going to depend on how you deal with the co-seismic offsets, how you deal with the post-seismic offsets. And it turns out that that's quite a challenging problem. I'll talk about that in a moment. So another big challenge before we get to that was calculating the uncertainties, something that is, again, everybody does this differently, probably, because there's no one single correct way to calculate uncertainties for INSAR time series and velocities. So here, what we decided to adopt is basically to do it the same way that it's done for GNSS. And these end up being the uncertainties for each of our velocity models, the consensus velocity models. And the reason we think they're reasonable is because they actually end up having higher uncertainties in regions where you would predict higher uncertainties, such as where there's more topography or decorrelation, and in dry, arid places where, where the motion is very well constrained, the uncertainties are low. Also, they're higher for ascending tracks than descending tracks, which is something that we've always observed and never have been really able to explain in this study area. So it makes sense, we think. But I will move on to the Ridgecrest results because they are probably the most interesting thing that we've done so far. So how do we deal, again, when you have an earthquake in the middle of our time series? Everybody has a different way of doing this, and so far we have just done a comparison between all of our different results. So a couple of the groups use kind of a physical model of a coseismic offset and plug that in as the earthquake and calculate the time series around it. There is the Scripps group have kind of an iterative approach of estimating the offset and then applying corrections and so on. There are two JPL groups now that did not agree on a method, so they're using different methods, which is interesting. It's great. So as you can see, the results are, there are two rows of results. What they are is they're the cumulative post-seismic deformation. So I took an observation right after the earthquake and up to 1 year after the earthquake. And you can see that the results from the different groups that have tried to make these time series can be quite different, different noise levels. There are certainly common features, such as you can see to the north of the big star. The big star is the epicenter, the hypocenter. There is a discontinuous feature in all of them. So there are common features, which is encouraging, but there are a lot of differences. And these are the differences that we are now exploring in terms of how people calculate time series across an earthquake, how they calculate their offsets and post-seismic deformation. Again, we did a time series comparison, and again, the results are variable. For some groups, the agreement is quite good. Others are more noisy. Overall, it looks fairly okay, fairly successful. We're kind of able to do that, but we are exploring what these differences mean in terms of what the best practices are for applying methods to calculating time series across an earthquake. I don't know how much time I have. I think I tried to go through this quickly.
You've got plenty of time.
Plenty of time, okay. Well, I don't have much more to say, so I would like to have more of a discussion. I'll just say that this exercise is not restricted to people who are from Southern California. If you want to join, we're always welcoming new people with their other methods who can come to our virtual meetings and argue with us about how their method is better. I love that. So please join us if you want. We have a lot of things planned. As David showed, we're trying to expand to cover more area. We're expanding down into Mexico as well as northward. We are trying to incorporate into our big time series some of the legacy data sets from ERS 1 and 2 and NVSAT. Most of our groups already have those results. It's just a matter of compiling them. Campaign GPS, ALOS. And of course, we're looking forward to new and upcoming missions from ESA and also NISAR. So that we will have longer continuous time series. We're looking forward to continuing our work on creating a time-dependent three-dimensional deformation field from a combination of GNSS and INSAR, and calculation of strain and strain rates. Of course, more research into best practices. We are transitioning for some of our pre-processing, just interferogram formation into cloud computing and automation. And of course, we'll have some workshops to actually get people to use our model and see what they think. So anyway, that's all I have, and I will welcome questions and criticism and things like that.
Thanks, Katya. So yeah, we do have time for some questions.
Sorry, thank you for a great talk there. And it's really great you're doing it's such an important aspect to get at the uncertainties. So my question is around those uncertainties. You've got one way by comparing 5 or so models, but then you're taking their uncertainties, and your slide that you showed had areas of the map with near zero uncertainties. So what do you plan to do with that kind of artifact of the assessment of the uncertainty level?
Okay, so I want to explain the areas of zero uncertainty first, and maybe that'll make more sense. They're not quite zero; they're close to zero. But so again, one of the reasons is because the time series there are quite dense. There are a lot of measurements, and the region is pretty dry, and so it's easy to measure, and there's not a lot of topography. But the other thing, of course, is that INSAR measurements are, at least in our case, always done with respect to a point. So of course, close to that point, the uncertainty will be very small, and far away from that point, it'll get bigger. That's what's happening. That's why you could see this, especially in track 166 right here. See, there's a patch of blue. That's where the reference point is. That's why they're so low.
Yes, and certainly that's what we find. So the best
Yep.
thing is to inflate those back up so that it's reference point independent, because then if you want to pass that on to other people, they don't have to worry about that. You have a more of a uniform approach to estimating the uncertainty across the area.
You don't think it's realistic that they're smaller there?
No, it's not. And if you then push that on to someone else, unless that subtlety of the referencing is meaningful to them, I think it gets lost, and you want a better estimate of the uncertainty. Because obviously weighting at 0.01 millimeters per year would really heavily weight that area.
Yeah.
So yeah, I think thinking about how you propagate that.
We've had a lot of arguments about this actual point. Do you use some kind of a function, like, it's decaying away from the...
Yes, there's a spatial variogram to just jack up that reference so it represents more something at tens of kilometers, yeah.
Okay, I'll try to convince them. Thanks.
Gee, next, I guess. The microphone will come.
It's my new favorite person. Hi.
Hello. Thanks for the great talk. Also on the uncertainty point, but I wasn't thinking about the referencing issue. I was thinking about whether your uncertainty map would match up with the difference between individual velocities and the consensus model. You showed this difference between them, and I wondered whether the areas of larger uncertainty are also where the difference is larger, and then whether the number match up as well.
Just to some extent, that's true, because the places where the differences are larger are just generally places where it's harder to process the data, right? So again, places where the topography is large, so there are more errors, more atmospherically related errors maybe. Places where there's more decorrelation. So to some extent that's true, and to some extent it's not. So yeah, they're different uncertainties. So I guess for time series, actually, we still do that thing where we, this approach is for velocities. For time series, we still do that thing where we just estimate kind of the variance between the different models and the deviation from the mean for each of the models. But yeah, and those are kind of the epistemic uncertainties. They're model-based uncertainties, as opposed to these ones are supposed to be more physical, except for that reference point issue.
Right, great. Maybe I missed it. When you produce the consensus model, do you just do a simple averaging, or do you do the weighted averaging based on the uncertainty maps? And whether all models have the same reference? Sorry.
We don't do weighted averaging, because what if one of the models has a large deviation from the mean in some place, but that one is actually right? Like, why would you prevent that? So we couldn't agree on a weighting scheme because of that, because we don't know what's right? If you know, come and tell us.
So yeah, both as a answer to that, and also just in support of what you're generally doing.
I like answers.
Sorry?
I like answers.
Okay. We have the exact same problem in statistical seismology with smooth seismicity models. I have coworkers that have convinced themselves that basically nobody's smooth seismicity model predicts any earthquake location more than a few years after it was made, unless you make it completely uniform. And they've proven that to be true in a lot of cases. And so what they've started doing is something called expert elicitation, where you grab We actually do this for seismic hazard models, but you can do this for smooth seismicity models. This was done for the Christchurch earthquake aftershocks. They grab a bunch of people's models, and then you do a process to evaluate how individual users are, like, so you get a separate team of people that are going to be your voting team, do a test process to evaluate who's overconfident and who's underconfident about their state of knowledge, then have them vote on which models they like, and you use those underconfident, overconfident metrics as your weighting. It's called
Wow.
classical method. Anyway, we use it in seismic hazard. And it's, I mean, it probably, a lot of it comes out 50-50, so, you know, your straight up averaging would be right about right. But that's how you, that's one way of getting, I mean, it's a subjective, but.
It's very interesting.
It's
Put it
the
to a
same.
vote. Okay, so everybody has to come to our meetings now and they can vote. Come on. Yes. Anyone else?
Were there any more questions? Tim, I think.
Sue has one.
I guess you said California and beyond, but to Southern California. A lot more challenging, I think, elsewhere in the world, where there's more vegetation and there's other challenges you don't have here, and it would be interesting to pick a different area as well, and obviously we'd be happy to be involved as well.
I am personally very interested. Actually, we have talked about it. We did talk about it, about getting people involved who are processing and doing research in other areas. And yeah, I think that that's a good way. We just haven't recruited anyone yet. So if you would like to be recruited, we'll be happy.
Well, if you picked.
Right, okay.
Well, this is
That's fair.
sponsored by SCEC.
And yeah.
So when we write the
And
proposal, it has to
GPL,
be
so.
SCEC focused.
Well, not anymore, but
Yeah,
they don't really care. Okay.
Andrew.
Just checking one of the points you said, it was the average of the velocities and the displacement series generally gave you the better fit to the GNSS,
Yeah,
broadly.
yeah.
Is that implying that the noise in them is basically random, or does anyone's method work better in a given area? Like, just
That's right, yeah.
someone's method is sometimes better in lowlands, someone else is working better in mountains, or is
Yeah.
it basically just random?
I mean, it's kind of hard to say, I guess, but yeah, I mean, I can show you that plot. You see how the individual models differ from each other, and some of them have quite large differences. And then when you average them together, you kind of get rid of these artifacts that are introduced just by individual approaches. And yeah, I agree that it could be interesting to look into, like, what exactly is causing all of that. And we have been doing some of that, but it's, for the most part, it's kind of hard to say, but it works.
Just on that point, I mean, I also thought that, I mean, you can't use the agreement with the GNSS to actually locally weight different models, so where one model is doing particularly well.
We have also thought of that's a lot of work, because you have to account for, like, again, the local effects, because some of the GNSS stations, they're capturing something that is super local, so we would have to actually really go in detail through the GNSS data to do that well.
Yeah, fair enough. All right, John, I think there's one talk that's actually not going to be given, so
Yeah,
we can stretch this out a little bit.
is Fernando Monterroso here, or someone from his group? Otherwise, we have plenty of time, but if he's here, we should move on.
We can make a community genetic model right here, right now.
So
one thing,
Oh, you are here?
Oh.
Is your talk uploaded?
Is your talk loaded? Okay.
Okay, in that case, we'll move on.
We didn't know this. We're very sorry. Thank you, everyone.
Right, do you want to take over?
All right, so the next talk is locus and types of seismic secondary fault slip during large magnitude earthquakes, and Henriette Sudhaus will present.
Okay, thank you. Yeah, thanks. So this is a small author group. Two of them, Vasiliki and John, are geologists, And Tilman is a master student at Kiel University. So I'm very happy for comments and so on, because many things, yeah, I'm coming up with. And I actually benefited already from comments last night during dinner, and also from EGU, from Shoni. So thanks for that. What? Yeah. Okay, synseismic secondary fault slip. I would like to make a comment based on an interferogram. So synseismic means we observe this in co-seismic interferograms. And you know the time resolution of interferograms is not that great. So synseismic means it's connected to the earthquake. How closely it's unsure. I think it's very closely, so maybe almost instantaneously, but this is maybe, we can argue about this. Secondary means it's not connected to the co-seismic signal from the earthquake, but it's actually, I think, a passive reaction, and it's a very small signal compared to the main one. So you can see here the arrows pointing to offset phase. So you have the feeling that the fringes are cut, and you can follow this sometimes really long kilometers, but it's a very small signal, so it's easily overlooked. And then we say fault slip, and I had the comment that this is maybe too liberally used. So it's an activation, it's a motion across a fault. Yeah, if this is fault slip in the meaning of stick slip, we cannot say. Yeah, and it's likely a very shallow feature. Okay, so this is a normal fault, is a signal of a normal faulting earthquake. It was a blind rupture, so we have no real surface trace, or if it's very hard to see. And the main signal is this concentric co-seismic signal. Yeah, but you can see this this offset. We move out a bit. So what is this offset? Where is it? Maybe we can have a look at thanks, at a more regional tectonics. So this is in Tibet, and you can see that's a kind of a pull-apart basin. And what has developed, according to literature, is the negative flower structure. So during this evolution, we have many, many faults that have been formed there and that can be reactivated. And I think this is what we are seeing here. This is the faults that are mapped here from the active faults of Eurasia database. This is not very detailed, of course, in this region. Oh, why does that? Oh, yeah. So going back to the signal. So we see there is an activation, and I can tell you, if you look in optical images, you can actually see morphological features, very faint ones, but they are there. Sometimes covered a bit by sediments. So to now look maybe at how does the fault move? Yeah, we make use of an ascending interferogram. This is the one that you see here. We unwrap this, we take a descending interferogram, unwrap this as well, and then we have seen also many examples of this. We derive from that east component and also an up component where we may have like north component contamination. So what you see here is the east displacement for this normal faulting earthquake. Yeah, so you can also see that this signal where the arrows are pointing is kind of tiny. I would quickly like to change perspective a bit. So we are making a profile across, so perpendicular to these fault structures. And I just show you here the east-west displacement. You can see a nice curve. This is the blue one. You can see some disruptions where there's maybe also some decorrelated areas, and we lose the signal. But you can see where the black line has the minimum. This is the vertical displacement. You can see this one little step. So this is actually where this signal that I've pointed out is before. And maybe just as a conceptual sketch, so we have a blind rupture. So we're looking at depth, and this blind rupture did not reach the surface. So we can call this a slip deficit at the surface, or maybe there's something else. And what we have at these secondary signals is something that, I would put like this. So it's not to scale. It's just to make the concept clear. They have to be shallow, otherwise they would have had a larger signal or longer wavelength. And what is interesting a bit here, when we think of some of the profiles, we think of seismogenic depths, we think of the loose surface. The question is a bit, of course, have these signals anything to do with the earthquake deformation cycle? Well, I think they have to do with that. Is they are part of this? The question is there any significance? Because they're really, really tiny, and this is something that I'm not sure. So we're talking about a phenomenon at the moment. Yeah? And I'm happy for ideas later on. Okay, we go back to the signal. What you see here is not the east component, but now I'm calculating the gradient in the east direction. This is I do this very simple. I take my displacement map in east displacement and I shift it by 2 pixels and I calculate the difference. Super puristic. And you can see, maybe I hope you can see these steps where the arrows are pointing. And in the northeast, you can see that the step is now something like a reddish line. This means that the pixels east of the fault have moved further east compared to west of the fault. So there's some kind of extension. And you can see that further down the line, so where there's this blue arrowhead, actually we have a blue line, so it's the other way around. And then we have again a red line. So we have a fault activation, but it changes the motion direction, which is very interesting. I would like to go to a different earthquake because this is nothing special, I think. But we are not looking at interferograms that closely anymore, and we now have these very nice interferograms with high coherence and so on. So we have been in Tibet, where the blue star is, and we move now to Greece. And I will start with an earthquake in central Greece, and I will have just one slide on an earthquake in Greece, in Crete, in 2021, both of them. So this is another normal faulting earthquake displacement signal. We have concentric features. It's partly blind, so you can see that we have a very high fringe rate in the southwest, and there's actually partly surface rupture. If you model this earthquake, this is a very simple rupture model, but it's constrained also by seismological data. Uniform slip, so you see this is the main rupture extension. The projection to the surface is relatively shallow, dipping to the northeast. And I mark there where I try to map the surface rupture, which is partly based on post-seismic data where it's much clearer. What you can also see apart from this predominant signal are again cut-off phase, so disrupted phase in a linear manner. This is one point is here. There's one interesting small bifurcation there. And we have another one here in this black box, also disruption of phase. And I would like to look a bit closer into this one. We have a disruption of phase, and we can unwrap the interferogram, we can unwrap the descending interferogram, and then we can again come up with maybe an up component. And this is what I'm showing you here on the next slide, and I'm drawing a profile across this fault. And what you can see is that you have towards the northeast, you have an upward motion that is increasing, so there's kind of a step across this linear feature, this fault, and in the east component, we have a less east motion on the northeast side. So there's also a compressionist signal. When you see the topography in the background, it's very clear that this, on the long term, this fault behaves as a normal fault. Yeah, so we have the mountains on the southwest side, and we have kind of a graben structure on the northeast side. So due to the earthquake, this fault was activated in a reverse sense. This is not, I mean, we have seen this also for the Ridgecrest earthquake, we see this for strike-slip earthquakes, but this seems to be also a common feature for normal faulting earthquakes, that we have these surface activations of fault structures that have maybe no friction at all. So when I take these measurements and I'm calculating here like a more compressional sense, a more extensional sense, I'm making the disclaimer here, the north component, we have no grip on this, right? So this is completely ignored, and this may be a real limitation and a weakness here. But let's pretend we have an extensional regime, and this is dip-slip poorly. So we can see that we have these fault activations that I've mapped. Some I've shown, the one in the south I've not shown. But there we have also a reversal of activation. So the question is, of course, if this is due to the co-seismic stress change, then we should be able to prove that, right? So let's see, can we use our strain maps to verify this? Well, the problem with strain and INSAR, so we have a strain vector, we can calculate the strain tensor, and we can calculate a dilation and see where we have extension and where we have compression. The problem is we don't have the north component. Yeah, and this is a very these are magnitude 6.3 earthquakes. We don't have pixel offsets or something like this for the north component. Sometimes they are small, so it's also hard with burst overlaps. But we can have a workaround. If we have a good rupture model, then we can predict the surface displacement. And it has been shown that for shear dislocations, actually the two components are very good to constrain shear dislocations. So the north component is not completely unconstrained. So this is so we're taking synthetic displacements and we're calculating strain and we calculate dilatation. So we will see some of these signals. So dilatation maps, positive means we have extension and negative means we have compression. So I'm jumping back to the Tibet earthquake. Yeah, you have seen these like reddish lines and bluish lines in this east-west gradient map. And this is here now with just normal faulting and thrust faulting signatures, the changes. And what is actually very interesting when you follow the fault from the northeast to the southwest, that you have this normal faulting activation in areas of extension and you have the thrust faulting activation or this compressional signal where there is compression. So this fits very nicely and is actually kind of a proof. You can also see that there's some things that are not quite matched. So I've in the map it looked like an extensional feature right in the middle. Maybe this is some unmapping problem or something, but there's also clear normal faulting activation at the site. Well, yes, there's some dilatation still. Yeah, so it fits quite nicely, despite the model that we use is just a simple rectangular fault. But it's at depth, so maybe you don't have more resolution for anything more complex. I'm jumping now to an earthquake in Crete. Yeah, it's a normal faulting earthquake. It's a blind normal faulting earthquake. There is a dominant normal fault that is mapped. This is the black fault outline that you can see. It runs north-south. It's a Castelli fault. And this earthquake we think it ruptured the Castelli fault at depth, but it did not really reach the surface, despite that we see also steps directly at the fault. These are the blue markers here. These are mappings by a student, also the fault model is done by a student. The interesting thing is that apart from this very prominent fault zone, we have some activations of fault perpendicular to this fault. And this is in a sedimentary basin. No faults are mapped there because they are covered by sediments, but we see disruption of phase, and this seems to be along a continuation of another fault system. So this is actually very interesting. So my geology colleagues said, great, we can map faults now that we haven't known of before. The interesting thing is that these faults, these perpendicular faults, they seem to stop quite at this similar point. They are a bit in the bluish areas where you say, actually they're clamping, right? We have more compression. But yeah, we use a very simple fault model. Maybe the signal would look different if we had something more complex, and then it would all fit perfectly. We're going back to the Central Greece earthquake. I hope you are still following me. So here again we have the mapped faults. The green ones are the synseismic activations, as we call it, and this is the predicted dilatation for this earthquake. And you can see that the surface rupture, this is the blue normal fault in the south, is perfectly sitting in this dilatation zone. We have also other activations, the one that is more to the west. We have in the very south the green line, the green fault activation that turns from south normal faulting to thrust. It actually turns to thrust where it starts to come into the bluish compression area. Very good. So this is nice. Above the fault, we have extensional activations seemingly that are in a compressional zone. This does not fit that well. And we have also this reversal of motion at this long fault to extension, also in the bluish regime where we don't expect this. So at EGU, Johnny pointed out, well, we could maybe, this model is constrained with displacement data and seismology, so it's good. And we, master student Tillman, he also tried to have a two-plane rupture model. Yeah, to say we take two planes, do we fit the signal better, of course. But the question is it justified to use more complex model? based on an informational criterion. And it turns out it's not. So the fit is better, but not that better that you can really justify that many more parameters in your optimization. So, but when we use this data and we calculate the dilatation, so this is so the first plane remains pretty much the same, but there's a second rupture plane that sits beneath this relatively shallow dipping plane, and that is antithetic. And now we have also an extension regime above the fault plane, and so this fits with the observation. Also, this very small extension regime sits in a very localized area of dilatation. So it looks like with this rupture model with extra data, which is basically gradient and very sensitive to surface things, we could argue that this is the better model. So I'm coming to the conclusion. So what we see is that faults react to earthquake at neighboring faults. So this is something that we intuitively would expect, and we can observe this with INSAR. We have 1 centimeter slip across kilometers. Try to map that in the field, yeah? So this is great. We can do this. So this synseismic fault activation, it releases a bit of stress, yeah, but it's tiny. So I'm not sure how significant this is. We can use this for fault mapping, and potentially one could use this to constrain some of the co-seismic models that we have to some extent, yeah, to say which one is better. Thank you very much.
I think we have time for 1 or 2 questions. It's a very interesting topic to me.
Thank you, very interesting talk. Have you considered the impact of shallow rheological variations in terms of concentrating the stresses? Because you're presumably looking at really very shallow features. And in the case of this earthquake in Greece, you've also got the Taverna Spacing, which is bounding, I think, the fault where you get this transition.
Sorry, I didn't get the last bit.
So you've got the sedimentary basin to the
Yes.
north of the fault where you have this transition, and the impact of that change in geology.
We haven't looked into this, but it's actually very interesting to say we have a lot of faults. Some of them, seem to be very weak and they react, and some of them are not. And then, yes, so we see also in the sedimentary basin that faults show up that cannot be mapped because there's some alluvial sediments across. So this is quite exciting for a geologist. But we haven't looked into this systematically. Yeah. That's a good idea.
1 more quick question, then we'll move on.
Hi, Henrietta. Do you think there could be a way to explain this by looking at the rupture propagation direction? So whether it goes from the bottom of the fault to the top or the top to the bottom, if that could affect these localized movements?
Possibly. I mean, so according to our model, the rupture started for this for this event on the bigger plane on the lower part and ruptured upwards. Yeah, I haven't looked into this into detail, and this nucleation point is not very well constrained, and the depth of the hypocenter from seismology is also not so very well constrained. So this is, yeah, but I keep this in mind. Thank you, Egbert.
Okay, I think we need to move on, but it's a really interesting topic. Thank you. Okay, the next talk is recovering the post-seismic slip of the 2019 Ridgecrest earthquakes using INSAR, a long-track burst overlap, interferometry, and GNSS measurements. And Yohai Majin will present the talk.
Thank you. That's not the right... Okay, thank you. I will show today our reconstruction of the post-seismic deformation field of the Ridgecrest earthquake. And this will be done with INSAR, GNSS data, and maybe most importantly, burst overlap interferometry. And I will try to show to you the importance of a long track measurements in northwest striking faults. So the Ridgecrest earthquake was a pair of foreshock, main shock earthquake, which occurred in 2019 in east of California, just north to the Garlock Fault. And in the lower panel, we can see the foreshock seismicity pattern, which was a pretty unique seismicity pattern of a perpendicular set of faults. And in a previous work, we showed that both of those faults has been ruptured during the foreshock earthquake. And in the upper panel, we can see the seismicity of the main shock. And from the seismicity and from slip solution, we can say that the faults that have been ruptured are predominantly the northwest striking faults. So this will be the main fault that will produce post-seismic signature. And we can see this when we're looking on the post-seismic signature as it's viewed from the GNSS network of California. And we can see the cumulative displacement of the first 5 months following the earthquake to the left. And we can see that it's agree with right lateral strike slip movement on the northwest striking fault. And to the right, we can see the two stations most close to the earthquake rupture. And not surprisingly, we can see that the post-seismic displacement is just a fraction of the co-seismic displacement. So when we're looking on the co-seismic event, just using regular interferometry is not a problem. But when you're moving to the post-seismic deformation, which is very small, using only line of sight interferometry, which is mostly sensitive to the east-west component of the deformation field, is becoming problematic. So to mitigate that problem, we will use a burst overlap interferometry, and this method is taking advantage of Sentinel-1 TOPS observation mode, and essentially Sentinel-1 is observing Earth in bursts, and each 2 consecutive bursts are overlapped by 10%, this creating 2 kilometer wide strips that viewed twice in each satellite pass, and they viewing those bursts in forward-looking and backward-looking geometry, and we can perform the following interferometric scheme. We can take the interferogram of the forward-looking and the interferogram of the backward-looking to get 2 interferograms in the light of sight of the backward and the forward-looking geometry, and then the interferogram of the interferograms to get the deformation in the flight direction of the satellite. So before jumping to talk about the post-seismic displacement, I want to show you the co-seismic displacement as it's viewed from the burst overlap interferometry. And here to the left, we can see the line of sight interferometry or traditional INSAR of the ascending track of the of Sentinel-1. And in the middle panel, we can see the burst overlap interferometry, and the profile in the right panel compare the two. So B3, which in the upper left corner, is comparing a burst that's crossing the fault, and we can see that the burst overlap interferometry in gray essentially showing us maybe the classical view of displacement perpendicular to strike slip fault with more than 2 meters of offset across the fault, where in the line of sight interferometer, we're seeing only 90 centimeters of offsets. And we can see meaningful deformation above the noise level in the burst overlap interferometry much farther than the fault. We can see maybe even in B7, so more than 70 kilometers away of the fault, but definitely in B6, we can see deformation above the noise level, where the line of sight interferometry is already well below the noise level. So this is giving us an example of the importance of the flight parallel component of the displacement field in the case of this earthquake. So in order to retrieve the post-seismic deformation, we perform a small baseline subset time series analysis, both for the ascending and the descending track. I will show mostly results from the ascending track as it has favorable geometry in compared to the fault geometry. And here are the cumulative displacement over the first 5 months following the Ridgecrest earthquake as it's viewed from a line of sight interferometry to the left and burst overlap interferometry to the right. So we can see that we do have some very substantial deformation in the line of sight, but those deformations are concentrated in places of fault geometry complexity. So they probably related to this geometry complexity and some poroelastic rebound processes. And to the right, we can see the burst overlap interferometry where we can see nicely the offset along the fault in burst B2 and B3. And we can also see that there is a significant amount of deformation of the fault in B4, so 10 kilometers out of the fault tips. So we can compare the post-seismic versus the co-seismic deformation, and we can see the post-seismic deformation in the burst overlap interferometry in the black dots, and we can see the bursts that crossing the fault are B2 and B3, and we can see that we have about 2 to 3 centimeters of offset, where in the co-seismic deformation we reaching 2 meters of offset across the fault. And we can also see that actually the maximum post-seismic deformation is lie in B4, so not across the fault trace, in almost 4 centimeters of displacement, and also some meaningful deformation in B5. And if we're comparing the post-maximum displacement to the co-maximum displacement, we're getting that the ratio between the post to the co-displacement are 10 times larger in B4 and B5. So we have something up there in the north that we will try to explain. So then we will move on to talk about the temporal evolution of the displacement field. And to the left, again, we can see the temporal evolution of the cumulative displacement of the burst overlap interferometry, now with the cumulative displacement of the GNSS. And to the right, we can see the temporal evolution of the displacement field. So we took the horizontal component of the GNSS data. The vertical component was too noisy, so we only took the horizontal component, and we project them to the satellite parallel, satellite perpendicular direction. And to the right, you can see a comparison between the burst overlap time series, a line of sight time series, and the GNSS data. And we can see that we have, where we have GNSS data, we have almost a perfect fit between the burst overlap interferometry and the GNSS data. And we have about 1 to 2 centimeters of offset between the GNSS data and the line of sight interferometry. This is giving us the vertical component of the displacement field in the line of sight. We also can see that the displacement that we see in the north is completely missed by the GNSS network. So both the GNSS network and the line of sight interferometry missed those displacement. And we can also fit some logarithmic function to the burst overlap interferometry. Are the pin curves. And we can see that we have a different decay rate between the bursts that crossing the fault and the bursts that are off fault. So we will try to compare those decaying rates with the seismicity rate. And here in the middle panel, we're seeing the post-seismic seismicity, or the aftershock following the Ridgecrest earthquake. But maybe before, I should mention that Ridgecrest co-seismic rupture ceased at the tip, so almost at the tip of the coastal geothermal area, which is an area with high heat flow, very shallow interseismic seismicity, so high transition between brittle and ductile crust. And we can see that the color are representing the distance from the coastal geothermal area. And to the left, we can see the normalized earthquake count in strips perpendicular to the fault. And we can see that that the seismicity rate is decaying faster as we're getting closer to coastal. We can see the same pattern when we're looking on the deformation. So the deformation is in the right panel. The dashed line are the same curved, pin curve line that we saw in the previous slide. And we can see that the blue line that represents burst 4, which is off the fault, is decaying faster than the red and green line that represent that the bursts that crossing the fault. And if we're looking on a co-located seismicity with the burst, so the polygons, the red, green, and blue polygon in the middle panel, and we're looking on the normalized earthquake count, we can see that where we have really co-located seismicity, in B2 and B3, we have almost a perfect agreement between the seismicity and the deformation. And in B4, where we don't have a really co-located seismicity, we do see the same pattern of decaying faster, but at a different rate. And finally, we will try to suggest some post-seismic sleep model to explain those observations. We will first suggest, or we will consider model 0, which consider only sleep along the faults that have been ruptured during the co-seismic sleep. This will be model 0. And then we search for an off-sleep transient with Monte Carlo Markov chain inversion scheme. This yielded two off-fault geometry 1 and 2, where 1 is a strike-slip fault, or it's both strike-slip and normal fault, but left lateral, so a mirror image to the fault that has been ruptured during the foreshock. And fault number 2 is predominantly normal fault. And you can see the slip distribution to the left, so mostly wrapping the co-seismic slip with model 2 needs some extra slip to the north to fit B4 and B5. And we can look also on the data to model fit. So generally, all the models are fitting the INSAR data similarly well, so they do succeed in modeling the general pattern of the formation, but do not succeed in fitting the near fault high deformation, which I mentioned earlier that they are probably related to poor elastic rebound, which we did not include in our model. And when we were talking on the burst overlap interferometry data to model fit, model 0 that consider only slip on the co-seismically ruptured faults, doing pretty poor job in fitting B5, where both model 2 and model 1 doing very good job in fitting this burst, and model 2 doing also very good job in fitting B4, and model 1 doing slightly better than model 0. And we can also try to compare our off-fault transient to the stress regime in that section of the fault, and this can be calculated out of the moment tensor catalog of Wang and Zhang Wen. So we can take the moment tensor catalog and transfer them to a stress regime in the upper right, and we can see that model 1 is agreeing very well with this stress regime, where model 2 not agreeing very well with the stress regime. So we conclude from the suggested model, we find model 1 the most probable. I think I will finish with showing the summary and taking questions, comments. Thank you.
Great, thanks. Well, we have time for a few questions. I mean, you're right on time there, so.
In some of the post-seismic interferograms, that something close to where your fault 1 was showing up as a obvious discontinuity in some of the interferograms. So I think that, did you notice that in your interferograms?
In the line of sight interferograms?
Yes, the regular line of sight interferograms.
Where did you see the uncontinuity?
Where you had put your fault 1.
I think I didn't notice it in my interferogram, but this could be a good result if I would.
Well, I'll ask a quick question about the effect of the COSO geothermal area. I guess you're implying that the crust or the crust there is behaving in a more viscoelastic manner because of the excess heat? Or?
Yeah, probably. That the reason also the formation and the seismicity is decaying faster.
More questions? We have time for one other question since we were about 5 minutes behind schedule before. Now we're catching up. There's one.
Thanks for the talk. Just quick question. How is the noise level to your burst overlap interferometry compared to classical interferometry? Do you see a big difference in terms of noise?
Sorry, I didn't get that.
The noise of your burst overlap interferometry compared to a standard interferometry, like is it more noisy, different frequencies of noise? Or?
So the burst overlap interferometry are more sensitive to coherency than traditional line of sight interferometry. But in other terms, they are more easy to handle, so they are blind, almost blind to atmospheric because of the interferometric scheme, which is an issue with the interferogram, the line of sight interferogram in that area. We did perform some empirical analysis of the noise by calculating the same time periods of burst overlap interferometry during the interseismic periods and expecting zero deformation, and we find they are sufficient.
It looks like you have a high frequency noise on this figure, for example.
That's due to the sensitivity to correlation of the burst overlap interferometry.
Okay, thanks. We'll have some time for more discussion this afternoon before the poster session, so keep your questions in mind. But let's move on to the final talk of this session, automatic seismic source model retrieval by exploiting the Sentinel-1 DNSAR co-seismic displacement maps available through the EPO SAR service. And Fernando Monterroso will present.
Okay. Okay, good morning, everyone, again. This is a pleasure to me again here to sharing my experience about this project working in IREA CNR with National Institute of Seismology and Geophysics in Italy. Basically, this job raises a summary about to do different algorithms that we development with automatic processing change with DINSAR products in EPOS catalog and a National Institute of Modeling and Automatic Modeling. So basically, with the outline of this presentation is, I will explain in general way to EPOS service that I already know. I explained the Monday about this service. After I will explain the automatic processing change in general way. I will explain how we can introduce the data setup, how function in general way in the aspects to nonlinear inversion, and how after the linear inversion to generate a slip distribution for every earthquake where they are working. I will show you some experimental results that are working in this project. More or less, we are tested with 100 earthquakes for the big catalogs, and also after I will explain the conclusion and future developments that we are approaching in the future. So, with as you know, we development automatic tool that provide the DINSAR products by EPOS service and thematic exploitation platform GeoHazard. We can check the code to visit the site, in this case the paper that I published in 2020. Basically, these automatic tools function every time there occurs an earthquake. The system catch the earthquake from different earthquake catalogs. We are working with USGS catalogs starting 5.5 until to the high magnitude, and National Institute of Geophysical Volcanology of Italy. Remember that we need to be in an institute to work in parallel with Department of Civil Protection, so we need to be operative in the seismic crisis, specifically in Italian territory. So basically, for Italian territory, we developed the algorithm that catch the earthquake for 4.0 until for 5.4. So this automatic tool works implemented in Amazon Web Service, and we produce every time there is a significant earthquake to different products. 2 days ago, we shared the experience with this automatic tool, with the automatic tool for Comet with Milan. We shared experience about to do how time of the download data, the Sentinel-1 data, and also the time for processing the DISOR results. So in this case, basically, we are processing and total more or less on the 600 earthquakes from 2015, the launch of the Sentinel-1A, until to September 2000 of this year, until yesterday, basically, we are producing 45,000 products and interference maps, loss displacement maps, and occurrence maps. So every time that this system now is available, so every time there is a course from the earthquake, we can access to information to the DISOR products. It's available in EPOS SAR system. So this is the char automatic chain implementation on automatic processing. Basically, we start to catch the information related to DISOR products from the EPOS SAR system and the focal mechanisms provided for different catalog of the seismology. In this case, we are provided with data USGS and also a National Institute in Jipu. So basically, I explained before, when I start the earthquake, this system in automatic way catch the information throughout the earthquake, start the processing, select the images, start the parallel space baseline, because it's the algorithm they use to produce this algorithm, produce this project, these products, and after to put all this information in the catalogs of the EPOS and geohazard expedition platform. So with using the focal mechanism, we create an expected, using the focal mechanism, the fault plane and the fault plane tool, we are basically extract the expected area affected by the ground displacement. So in this case, we create a small bounding box that we suppose that maybe occurs the significant deformation of the area of earthquake. So in this case, this is an example for, in this case, with the improvements that we performed on the SBAS algorithm specifically to earthquakes. In this case, this is an example from Badran earthquake in Iran in 2021 in 5.8 magnitude. You can see here the interference, the ascending and descending interference. So basically, with the bounding box expected with automatic for the focal mechanism, we select the area and we cut just the area for the unwrapping phase. So it's not necessary, basically, in this case, let me say, works with all the descent of the Sentinel-1. Just we select the area of interest with supported deformation area. So we are, in this case, the input information to do automatic modeling. In this case, there are different criteria to select the products of Sentinel. These are products. In this case, the first criteria is that we have to know the number of ascending and descending orbits using the inversion must to be the same in this case. Just for example, of the earthquake, a cover just for the one orbit, automatically the system select the co-seismic event of this track. So if we have the system of the automatic tool processing of the earthquakes basically works and produce in real time two co-seismic, these are co-seismic products. So using the two for 3 images. In this case, to select which interference, with loss displacement map, we need to select the short temporal baseline for every available track. In this case, if we have two co-seismic interference, we select, in this case, the short temporal baseline. So after to select, we select, in this case, the interference that has more current points in the area of interest. The other input parameter that we need to do to work in this algorithm is the loss unique vector files and digital elevation model provided by SRATM model. So we have input the loss displacement maps, we have the loss unique vector files, and we have the depth of this area of interest. So after to select the data, after to generate and start the input processing, we start with the nonlinear inversion. It's important to take account that this algorithm just function on this is a development just for the one foul source mechanism fault. So it's not, for example, if we apply this algorithm to of the earthquake, the Turkey earthquake in the past February, the automatic tool failed because just this automatic tool uses work with the one-fold parameter. So the nonlinear optimization is defined for the fold location, geometry, and rupture mechanisms to when you sleep, uniform sleep. This is basically the aiming of the nonlinear inversion. The nonlinear inversion works on also the refined source and coarse source. So this is basically how the function, the parameters. The first one, we are the source know the input insert products. We have the focal mechanism parameters, so we start to define the constraints. In this case, for defining constraints, we work on the range intervals for every source parameters. We select the fold dimension, the position of the fold, the depth, orientation, take, and sleep. After to define the constraint, you start to the nonlinear optimization. In this case, we start the nonlinear optimization to find the best fit solution. In this case, a nonlinear inversion fold, using the Lambert of Market scheme for marketing in 1963. Okay, so the algorithm tried to do obtain the constraints using the different parameters like the available in with Simone Azzori in 2018 on the paper of Mexico. One of the parameters is the digital elevation model for the production of the sleep. For these aspects, I suggest you to visit the paper of two of them are more parameters in this case. So basically, after to select or create the first best solution source, there are different criteria to define the base source. In this case, the first parameters is constrained and corresponding to use with nonlinear optimization. All the parameters as constrained and they have best fit values with the minimum and maximum ranges. The direction of the sleep vector and the treated space different from that of the focal mechanism, more than 5.5 degrees from the foul. Okay, after to select, let me say that the respect of these different criteria parameters, we start to perform the more or less 30 iteration by default. If the process comes okay, the algorithm starts to function the linear optimization. So the linear optimization, basically, the objective is to retrieve the distribution of the shared dislocation of overfold plane identified by nonlinear inversion I explained before. So the first parameters for the nonlinear inversion is the B4 solution I explained before and the source optimization to the subdivide the different page of the fold on the fold and the sleep. So in this case, we need to extension of the length of the width of the feed source. We have the fold the plane of subdivision of the number of different page, more or less in the area of the fold mechanism. So, and after we work with this linear system. This linear system basically works to the parameters, the epsilon exchange for the small thing of the area of the sleep. So there are different values to this equation. Basically, the M is the vector of the sleep values, the D is the vector of the observation, and the G is basically the matrix of the sign values. The M, I will explain in the next slide how we select the matrix and division in G. So basically, subdivision page, we need to bear on numbers of very different page of the area of the mechanism of sleep. And we define different values in this case to define the matrix G. For define the matrix G, we basically define the number of inversion points that these inversion points comes for the loss displacement mass produced by insert products and subdivide for the page of the subdivision. In this case, the page subdivision is of the 100 of 1,000 page. So define of the stress consistent, basically the epsilon for a strain deformation system is basically of these values. I don't want specific details about this part because obviously this part concerns of all the geophysics aspect of the algorithm. So if you want more information about this aspect, you can check the paper that I will show you after at the finish of the presentation. So after to define of these models, we need to start to take different criteria to select to the data fit model, ruggedness, the curve characterization, and define for the specific event field of fit max and minimum to worsen the best fits of the values respectively. The damping factor is to set values corresponding to 95%, of the field ferment. In this case, the Fallon factor is in this equation. So we have defined the matrix in value of G. We have the value of D. So it's basically to find the value of M for arrive to a slip distribution of the linear inversion aspect. So obviously, we need to establishment the algorithm is a completely automatic and unsupervised result, cannot be shared with scientific community without any validation. So the National Institute of Geophysics Volcanology in Italy have the different experts that are working in this project, trying to validate the products of the automatic linear inversion. So basically, this is an example of the results of earthquake in Ethiopia. We are experimenting results for more or less 99 earthquakes tested for magnitude 5.5 until to 8.2. In these cases, we are using the earthquake catalog of the EPOS project. And just we are working with the small magnitude of 5.5 earthquake occurred in Umbre in Italy. So, for all these cases, basically 16 cases, 16 earthquakes, let me say, valid, but no, it's not visible the consistent pattern. So we select, in this case, just 16 earthquakes of these 99 earthquakes, but there is not valid and consistent pattern. The second 6 cases with the consistent is very, very small, so the signal was small, so it's not possible to select, let me say, the bounding box using the focal mechanism parameter. So in this case, it's discard these 6 earthquakes. And 6 cases with the rupture of different faults, significant the Hawaiian events of Amblin earthquake in New Zealand. In this case, the algorithm followed because obviously we have more or less two-fourths of distribute in the interference. So in the loss displacement mass, it's not possible to start to do nonlinear inversion. And 11 cases, the modeling failed because there are displacement mass were affected by strong decorrelation. Remember that with EPOS SAR automatic tool, we don't discard the atmospheric effects because obviously we produce 2 cosmic interference. So to be sure that signal we tend to see in the interference is related to the deformation pattern in the area of interest. So in this case, 11 cases of the modeling failing because of displacement maps is affected by the strong decorrelation, let me say, of vegetation of atmospheric effects. So, and 60 cases, more or less, the 16% of the results, and in this case, the experimental results in modeling, processing is used faithfully, and end when the retrieval of the variable slip distribution. This is basically the map that represents the significant earthquakes. If we ask more or less why we select these earthquakes, basically we are based on to select these earthquakes dependently of the signal of the deformation pattern in the interferogram, the cosmic interferogram, and the loss displacement map. So this is some results on the slip distribution of different significant earthquakes that you select for the top of the catalog. And up to this moment, at the past Saturday, we are experimenting the seismic races in Morocco. So I show you these interference on the past Monday to show you that this cosmic interference will produce the loss displacement maps for the descending area of the Morocco earthquake. So in automatic, when I spoke and when I explained you the civil protection tools that we developed and I explained the past Monday, and the last moment, the slip distribution start to work in an automatic way. So basically, we need to be in IRACNR with support to civil protection. We need to be operative. So in this case, this automatic tool chart, the focus is focused to generate information in operative way. You can see the Twitter. I posted the Twitter, and in the same time, Simone Azzori, this is the colleague that works, and then they said, is the scientific that developed the algorithm to implementation post the distribution in the real time after the occurrence of the disinterference. So this is the paper that we can check. This is automatic seismic modeling source of the insert displacement. Basically, this works. This job joined the different efforts for researching IRACNR, experts in INSAR technique, and National Institute of Geophysics and Volcanology, the as experts in modeling source. So the conclusions about this and future advances that we are working now with this project is basically we create an instrument for quick and robust identification of the source parameters after of earthquake. Remember that I explained again that this automatic tool just works on the fall mechanism. So we developed an active service with the future magnitude 5.5 event of the global scale, and obviously the magnitude of the 4.0 until to 5.4 of European territory, just for study Italian cases. And the future, obviously, the extension of the catalog to all the sources detected for the INSAR Science 2015. We have, I explained before, we are processed more or less 605 earthquakes. So we have more or less 45,000 products, so that we can create a big extension catalog about to do all these earthquakes that I performed to these products. So we are consolidation of the formats and metadata with EPOS now. Still, we are working on define the metadata parameters to put the result of the automatic modeling and with EPOS. So still, we are working to define the metadata to put this information in EPOS SAR system, and obviously publish it to validate in the scientific community. And we are assisting the preparation for incoming SAR missions like NISAR, NASA ISRO, Roselle, Sentinel-1C. So we are here to wait for this future constellation to automatize and also to produce to this kind of results. So the extension of the LCLT, the extension to multiply source to modeling with artificial intelligence. We are working on to recognize basically the parameters to define, using the interference artificial intelligence to recognize the pattern deformation with using the interference. So this is all we can check here, the paper that published in the past August, the catalog sources, we can also access to all the information to all the more or less 100 cases that we are studying, and the catalog of the EPOS SAR service. I have in my email and Twitter from Simone Azzori and me that were the experts that we are working in this job. This is all. Thank you. Thank you very much.
Great. Thank you. We have time for a few questions.
Thank you. For the 60 successful cases, were they fully automatic or were there some intervention still?
Okay, basically, these 60 cases all are functioning in an automatic way. But when I explain the presentation, the experts in geophysics area check that really validate the parameters, so this is okay to produce the Lipps distribution. So nothing is in automatic because obviously we need to check if really the information that we are publishing in the scientific community is very effective. So we need to check before to publish something.
You showed one example where you said you could not really constrain the fault parameters because the signal was really small. Yeah, but it was clearly visible. And your catalog is meant to complement, I guess, the seismic catalogs that we have. I mean, it's building up on this, but it adds information. And one of the crucial information for shallow earthquakes is depth. So I'm wondering, so it's actually sad, right, that this is disregarded because we can say that it's not very shallow because the signal is very small. Yeah?
Yes.
So you can give constraints on the depth. If there's no mechanism, or you can say I don't know the strike or slip. So how do you deal with these? If there's something not constrained but other parameters are constrained, it would be very valuable. Are you thinking about changing this in the future?
Yes, obviously. For example, we are working with, for example, National Institute of Geophysics and Volcanology catalog that basically we are working with, we are processing earthquakes more or less the 4.0 to 5.6. The automatic faults create the really small bounding box, so sometimes it's difficult to model in this data because it's not sane also, and also because we are working with the Sentinel-1. We can consider the Sentinel-1, the pixel diameter is a little bit high to detect, let me say, these fault parameters for these small earthquakes. So we are experimented the work in the automatic processing of the
Oh.
Yes. So you said you're validating it before it is put online. I think it is, if I understood this right, I think it would be it would be useful just to produce something, put something out as fast as possible without having anybody look at it and just annotate it. Nobody has looked at it, and then it can be updated.
Sorry, can you repeat me again, please?
I mean, first to put something out as soon as possible without
yes.
having it validated, and you just say
yes, obviously. Every time there occurs the earthquake and you see the signal by the interferogram, we know that this earthquake, we need to create the automatic mode, the start of automatic modeling to see really if it's necessary to change some parameters. If it's not necessary to change parameters to define we can publish this information.
Yeah, I just want to make the point. I think it is important to have something out as fast as possible, even if it is not 100% right.
Yeah.
Great. I think we ought to wrap this up because we have time for discussion again this afternoon before the poster session, but very interesting results. Yeah.
Thank you very much. About this occasion, thank you very much for all, and also for Simone Azzori, that is the person that basically developed all the automatic modeling that we work together. So thank you very much for your attention.
Okay, and let's thank all the speakers for their interesting talks.